It's climate change adaptation. This is something that we at Ecoten do. I'm going to quickly check if, yeah, okay, it does work. Yeah, sorry, I had to test this a little bit. So yeah, at Ecoten, we're basically working as consultants and data providers to cities, and we help them to design cities in a way that is resilient to climate change impacts, more specifically to that of extreme heat events that we are seeing now more than ever. This year has been record-breaking temperatures across, and cities have particularly felt it during the summer. And we are trying. What we are trying to do in the two case studies I will be showing you is how exactly we help the cities to use data from various sources to make effective planning on how to cool down those cities. And in the first case, I will be showing you the case of Vienna. That was our first case. And what we did for them in 2019, what we are calling now the Urban Heat Vulnerability Assessment. So the purpose of the Urban Heat Vulnerability Assessment is to help cities to identify which parts of the cities are most vulnerable to extreme heat and which parts require immediate intervention from the cities to protect its population from urban heat during heat wave seasons. And this is a project that we do for cities on a city scale. It's a comparative project. And for doing this kind of an analysis, we use various technologies like what we say space technology, fancier word, Earth observation technology. Some of the cities I know are already using this technology in their respective data-driven program. I believe Izmir is using it. I've seen some of their work over there, and we'll discuss this later. But we are using Copernicus and NASA data to help identify these hotspots. Furthermore, we are also taking data from the ground, usually from the census program of each city or country, to collect information about the population demographics that are on the ground. And this is basically to address the vulnerable populations to extreme heat events and try to use it to identify the hotspots with respect to the population. And we also take into account the climate data that's available through the various climate simulations that the IPCC has done and has presented to the world with respect to global climate. And this is actually important for us as well. So while we are using while we're gathering a lot of information, a lot of data from this technology, we are doing this in a way where all of this technology will benefit the city to make climate adaptation. And for that, we have deployed a framework, which is also recommended by IPCC, on the measurement of vulnerability to climate change impacts. In our case, it's a city, and the climate change impact is extreme heat events. And that is what I'm going to show you right now. And according to the IPCC reports, vulnerability is a definition of three components: exposure, sensitivity, and adaptive capacity. And within this framework, we have used all the data that I mentioned earlier to quantitatively measure these indicators, these components. So first, for the city of Vienna, we have created an exposure index ranging from 0 to 1, which is basically derived from the surface temperatures that we are able to obtain from satellites, as well as the climate data where we can monitor the number of heat days that a city goes through during the heat wave or summer period. And this is annual. We also take into account the vulnerable population, as I mentioned. In the case of Vienna, as well as most other European cities, I think the vulnerable age group in this case is the very elderly people. They're most affected by extreme heat, and also the very young, that is below 14. And for the elderly, it's above 65 usually. And we take the population density and we map it, and we again normalize it to a value from 0 to 1. We keep all these things constant. And finally, we have the adaptive capacity. And this is the most important part, because exposure and sensitivity are components which contribute to the impact of extreme heat events. So exposure is a direct impact. What's the, in this case, the effect of extreme heat? Sensitivity is how much the system, in this case, the city, is able to absorb the impact that is caused by exposure. So this contributes to the overall impact of the city. Adaptive capacity is what actually counters that. So we know from various scientific validation that blue-green infrastructure, namely parks, green areas, trees, water bodies, moisture, all of these contribute to bring down the temperature of in a city to extreme heat events, and also bring down the urban heat island effect. And we are able to monitor that using satellites as well. And this is actually thanks to the Copernicus program. They have a wonderful amount of data for that. And while we have these three components together, we will combine them to create what we call the urban heat vulnerability map. As you can see, this colorful map of Vienna, and it is showing what we call the urban heat vulnerability index, again, ranging from 0 to 1. 0 being areas which are not vulnerable at all. That means that they don't get really hot during summer. Not a lot of vulnerable people are living there, and there's plenty of blue-green infrastructure there to not be affected by extreme heat. The indicator for 1, the red areas, are in fact the quite opposite as shown. And what's interesting to see here in this map, and what was discovered, is that usually in most European cities where you have the center of the city as the hottest area, because that's where the city center, a lot of activities are, and it's also the most urbanized area. In fact, it is not that area that is most vulnerable, because not a lot of people tend to live in those areas, especially the vulnerable people. In the case of Vienna, you can see that it's really not the cluster that is in the very center of the city, but rather the periphery of the city, which is around where, in fact, the most of the elderly people are living. And moreover, there are certain areas, if you just make a thermal image of the map, there are certain areas which will get heat up because there is just a big brown field there. If you see in the north of the, in the south of the city, there are some areas which are just blank, they're brown field, and in the thermal image, you will see these places getting really hot. But again, nobody lives there. So while that doesn't mean you cannot take action in it, but if you want to take effective action to protect the population immediately, you need to look at the sensitivity of the city. So that is the key point of this map. And this is the short technical side of this map. But what I really want to show you is what impact this map had on the policy that was made by Vienna. After this map was released to the public, the city used this map to identify 23 districts and created a project where they would actually try to implement some pilot case studies and using blue-green infrastructure, reducing parking spaces, putting humidifiers and water fountains in some of these areas to bring down the temperatures in these districts. So this is actually projects that the city has taken to mitigate this, and using the urban heat vulnerability map. And this is really interesting. This was started by the city of Vienna, and they call it the Kohlestraßen Plus project. My pronunciation may not be the best for this, but please forgive me for that, for the German speakers here. Uh, but this was received quite well from the city, and the political impact of this was really something else. When the map was released, Twitter went wild. People all of a sudden started saying, "Hey, I live in this part. What is the city doing?" And Vienna is known to have a very high quality of life. Like, what is the city doing to protect this and protect my area? And things just exploded, and the media took it, so both social and mainstream, and it started a political debate over climate action in the city. And that's where the Cool Street Plus project actually started. So this had a major impact on the policy in the city. And that's basically what we like to see as well, and we want to encourage other cities to do. That's our mission, and this was really, really encouraging for us. Just a quick overview of what kind of action is this tool is dedicated to. It's basically the use, like since we are taking in adaptive capacity, the level of blue-green infrastructure, we want to encourage the city to improve its adaptive capacity by measuring their blue-green infrastructure and increasing the amount of blue-green infrastructure to bring down the temperature. We've already seen from the satellite images that it works, and there's proof for that right here. So we're trying to move cities from being in the 2008 scenario to the 2020 scenario, using all the various different techniques to do so. And that brings me to my next case. Before I do that, I also want to mention that this framework that I mentioned, the exposure sensitivity and adaptive capacity, it really isn't restricted to the very specific data sets that I've mentioned here, because for Prague, for example, we did a similar assessment, and we took a very different data set. And for Prague, it was the sensitivity was more about the number of people who are taking the public transport stop within a in a particular stop. And the idea was to understand the vulnerability of those people, because we do public transport is quite good in Prague, and we do use it a lot over there. So during summertime, the people who are using it are quite exposed because they do use it a lot. And we did a similar assessment for them. Instead of using the elderly people, we used a very different kind of data and combined it with the satellite images, and we produced a very similar kind of map, which also showed that my house was also in a vulnerable district, and I did see the city making a lot of changes in those areas as well, which was, again, very gratifying. And yeah, we've been doing this for quite some time now. I will just move forward from here, because there's one more case that I want to share with you, both in Prague and Helsinki, and this is the second part of what we do. The first part, the vulnerability assessment, is just to identify which parts of cities are most vulnerable to extreme heat. But we also go one step forward, and this is one that is more connected to the digital twin, because we actually work in the 3D models, as you can see from this picture itself. And what we do is we take a closer look into the areas that are being vulnerable, and we try to understand why exactly is that place behaving in that way, using the physics knowledge, the knowledge of physics and urban environmental sciences that we already know. So for that, as I mentioned, we propose, and architects and urban planners are already working a lot on this topic, and they already know about the blue-green infrastructure and its capacity to reduce the temperatures. But how exactly do you implement that in a given urban area? Putting trees everywhere in the city could even counteract the effect that you intended it, because it blocks wind and it blocks circulation. So in order to understand the exact impact of blue, green, and white infrastructure, white being the color of the building, you need to know this impact before you actually spend a lot of money in building it, and that is where the implementation of digital twins come in. And one of the definitions I saw was about that you've written in the chat was about the sandbox, and having a risk-free environment to actually predict something. I think this is a very good definition and a very good case for that, actually, because in this simulation you can see the impact of these strategies before they actually are implemented. That's exactly what I'm going to show. So just a quick overview of the technology we are using. The technology is basically a tool which is able to calculate various different components, air temperature over time, humidity, wind speed, and solar radiation. We do that in a 3D scale, and we also calculate something called the Universal Thermal Climate Index, which is just a very complex name for what I like to call the felt temperature. And this is very important because felt temperature, just by the name of it, it's the temperature that human beings perceive when they're outside. Like, for example, I am right now here, and I go out and I know that the temperature is going to be 25 because of thermometers, but because of the humidity, I will feel it's like 30 degrees. And this is a very important measure for this. And this is basically the measure that we're able to produce in the data format for the digital twin that we create for our customers. Okay, we'll skip this. So for that, we create 3D models. Sometimes they're given to us. We take the weather data. We study the materials that are being used, the surface profiles of each surface within a 3D model of the area, and then we start simulating using the various different models. I'm not going to describe these models, this will take some time, but some of you may be familiar with this already, CFD, thermal modeling, radiation modeling, these are not new. And then we produce the results that I mentioned before. And this is kind of how the result technically looks like in a digital twin platform. You have data in line, you have data in points in the 3D sphere. So basically, as a user, you can do whatever analysis you would like to make for any part of the city, any cross section you want, you can do it. You can study any specific point, whether it's on the surface or above that, you can do all of that, and that is the point of making these urban microclimate simulations. So let's dive into it. We are usually using, I mean, this is something that just want to mention because it's always very complex with simulations. They're very complex computations, and we need to make sure that we have the right level of details for the 3D model. Ideally, we work with LOD2, but we can work with others as well. And this is what it looks like basically in the beginning when we are making the 3D models. Yeah, and for our information, for the data that we are producing with these simulations, they are usually provided in meshes. As you could see here, the triangles that you can see in these pictures on the right side, these are where the unit data is being provided to you. And what is an advantage for our software is that we can actually control the size. So if you, some of you may ask, like, at what config or what resolution we can produce the data, to answer that question, any really depends on which area you want to focus on. We can control the resolution entirely. But of course, if the resolution is very high, it will take more time for the simulation. I get this question a lot, so I'm just going to answer that here. And that's it, basically. Let me show you the simulation case study for an area in Helsinki that we did. You can see the variation over time. Please keep moving. Okay, it's a little slow. Are you able to? Yeah, so you're able to see. So you can see over time, as hours change, we can show the results of the simulation. Air temperature, relative humidity, latent flux is just a measure of evaporation, so basically evapotranspiration. So it's basically how much moisture is being released into the atmosphere. And this is a very, 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 very important nature-based component of cooling down urban microclimates. This is super, super important. And of course, the wind simulation as well. Particularly, like, these are the four components that are so important to study and to have for cities to assess existing or even new urban design strategies. And with these four components, we further calculate what I call the felt temperatures, and the felt temperatures look more like this. It's definitely on the 2D scale, and you can see this is a case study from our Prague project that we did last year, where we have made like a simulation of a really big area, almost an entire district, and we have simulated it for like 7 days altogether. I'm not going. I'm showing you all on many of these days together, but over time you will see. I'm just going to transition. You can see the results. Yeah, but there's more available on that. This data is available out there, and we know that the city is using it, and I'll show you exactly what kind of results that actually come out of come out of this simulation based on urban planning. So the area that I showed in Prague, actually, it's this one, and it's right next to the river. And what happens is that the objective actually was to see how the wind would come in and cool down this area. Right now it's a brownfield, there's nothing there. But this new design, we want to see how the wind interacts with it and how it varies the temperature. So what happened here is, in fact, is that they have this row of trees here, which they put, thinking that I guess that the trees are good for the cooling, but in fact it was blocking the wind from the river. So that's not a good thing, and that's very important because if there's no wind circulation, nothing is going to happen here. So we told them to remove that. We saw that in the simulation that wind is in fact being blocked the wind, by these trees. So we told them not to do that. And also in this area, this little corridor here, I'm not sure if you could see my mouse. I hope you can. Um, yeah, okay, cool. So in this corridor, again, it's full of row of trees, and again, it's blocking the wind. And this is super important because this is a main square here, and there is a big marketplace here. From an I'm talking about the urban side, a big open market here, and we want the wind to come through this channel, and then kind of infiltrate into this area. But because of the trees, it's not happening. So this is very important. We also told them, obviously, that you should not have black color or dark colored buildings in this area because this area particularly will get really hot. There are corridors here, and if you have dark colored paint for the buildings, it will absorb a lot of sun and it will not release at night. The urban heat island here will be phenomenal. So we told them I mean, from the simulations, we saw that this area needs to improve itself. And also in this area, you have a bunch of parking spaces, which is quite isolated. This immediately created a little mini urban heat island within this area, which wouldn't be known otherwise. And we told them to change that a little bit. So these are some of the applications of our simulations in an urban design, and we will see, of course, how this will be. This is currently under construction, and this is actually what we are planning to work with it in PSEC. We've already know the place. We're proceeding with that. But beyond that, there are many other cases that we have done for simulations. We just want to kind of showcase some of the other ways in which we use these simulations. For example, here you have a campus area which is which has no blue-green infrastructure, and you have one with green roofs, green walls, water bodies, everything, and you can very clearly see the temperature difference between the two. So this really is a proof for the decision makers to really implement blue-green infrastructure into this, and in a very effective way as well. Yeah, sorry, I went a bit ahead of myself. This is just showing the blue-green infrastructure. And funny enough, there is another funny example here. This area here is actually the same area as here. And in here you have, on the left side, you have this building, which is actually a brewery. And the client was concerned whether the smell of the brewery would actually come into this public area. And that would not be well because they want to make cafes out here. And we simulated that in this 3D model, and turns out that it doesn't happen. That's a good news for the people who are actually going to be setting up cafes here, because nobody wants that smell to come into that area. Beyond that, what is also interesting with our digital twin approach is that we can actually take any type of 3D models, because we work with architects and they come up with sometimes the craziest designs out there, and it becomes a little bit complicated, but we can actually simulate all these crazy designs out there, and especially with the wind, it really works well. And I will quickly jump back a little bit. Yeah. We built scenarios for implementing urban design strategies, like, for example, here, again, back to Prague, you have 4 different scenarios, all modeled in 3D, where you have lighter color paint and darker color paint, and you have trees and no trees in these cases. And these 4 scenarios represent very distinct urban design strategies, a combination of, in this case, 2 parameters, but usually in actual application, there is a lot more out here. So, but we are able to simulate all these multiple scenarios altogether. And the way it's being used, this model, as a decision-making tool is exactly like this. You have the central building. You have a decision to make whether you want to put a row of trees here or a row of trees here. Trees are expensive. They consume a lot of resources. You cannot build them everywhere. And so in order to know which area to build the trees, we simulated and we got the result from the felt temperature, as you could see. And the conclusion of this is that if you build a tree, if you build this tree over in this direction, based on the wind profile and the thermal temperature, the person standing here in this square will avoid extreme heat stress for a few hours as compared to putting the trees out here. So two scenarios and two very specific cases, and you can see a very nice comparative case of how the information that is provided from the simulations can actually help you to make this decision effectively before spending so much money to implement these design strategies. And that is basically the final thing I have in the case study. I just want to show you some very basic visualization of how the data is being integrated into digital twin platforms for cities. This is in Helsinki. They have their own model out there, and they're using this the model and the results that we provide. Both in 3D. This is 3D. This looks kind of funny, but it's actually point data which is floating around in the air, and this is a 2D, which is on the surface profiles, as you could see. And yeah, we provide this kind of data for the city as well, as you could see, various different formats, because we want to support the digital twin platform. And that's pretty much all I have for my case study in both the urban heat vulnerability assessment and the microclimate simulations result.